next speaker is, let's see, Mr. Hoessein Alkisaei. You're coming from that direction. Welcome. Structural engineer and lecturer also at the Department of Applied Mechanics, Civil Engineering at Delft University of Technology. Yeah. So your presentation will be about glass bottle columns. The floor is yours.
Yeah, thank you very much. All right. Good afternoon, everyone. Welcome, and thanks for having me here. Thanks for the introduction. My name is indeed Hoessein Alkisaei. This presentation will be based on a master thesis of a student at the university, Yunus Machi. But of course, in the end, it's a joint collaboration between the whole committee, which consists of Professor Louter, Chris Notenboom, Clarissa, and me. And the whole idea behind this, I will discuss that in a second with you. Of course, the two institutes of TU Delft and American Glass Research have provided their facilities to use during this research. And I will dive into that in a couple of minutes later. The whole idea is that we produce a lot of waste around the world. And we started off like, could we use that waste again to plant it again in the construction of our buildings? Can we use waste to create buildings and elements of structural usage for these things? So we came up with, well, this is what I will present at the end, of course. So we came up with the idea, can we create columns made out of beer bottles? Very simple, yeah? So we made eventually a prototype, and this is the result, which is standing at the moment at the university. But before diving into how this is done, I will want to give you some context. So the context is the following thing. We produce quite a lot of glass bottles in Europe, but around the world there's a lot of production of glass bottles. But the recycling of it, the reusage of it, is quite little and minimum. And what happens is that these bottles are usually dumped or placed in rural areas in the world, African countries, Asian countries, Southern American, and more. Now what happens over there is that these countries, the local communities, they use these bottles and start building homes, shelter, some other structural elements and buildings. And as you can see here, there are beautiful images from Thailand, from Brazil, from Southern American countries, and also African ones. And these are good examples. These are beautiful homes. But you have also other examples of these which are less good and just done by young people, people who are living in poverty, etc. So the thing is that we don't have engineering rules or formulas or practices which use waste to create homes, for instance, or other structures. So that's where the idea came from, and that's what we wanted to discuss further. Now, we can, if I go back to the previous slide, what you see here are, of course, columns, you see walls, you could also see floors, imagined floors, etc. And we wanted to focus on one of these elements, which is the structural columns. And so we came up with like, how can we create or design structural columns made out of glass bottles? And preferably, of course, glass bottles which are used. So not we produce glass bottles and then we implement them directly in the buildings. No, used glass bottles. And I want to dive into that in 4 sections. The first thing is the mechanical behavior, then moving on to the connections, then to the configurations and the limitations of these elements. So the mechanical behavior, and I'm going to focus here on a single bottle. We're here at the glass conference, of course. So we're walking around with a lot of glass experts here. But the following is, I think, quite general information. The glass strength of a glass bottle is, of course, strongly dependent on the damage. So as soon as there's a small scratch or something, this could induce or give an introduction to more damage within the glass bottle. It is weak in tension, of course. Once you give it some pressure, it has a lot of fractures, or it could generate a lot of fractures in the shoulder and the heel of a bottle. And the bottle thickness is also of utter importance for the performance of one single bottle. Now, we have performed some finite element analysis in order to see if this indeed validates what we predicted, and luckily for us, it did. We can see here the red rings are where the highest concentration of tensile forces and stresses combined and come together. That's also where like the biggest fracture happens during testing and pressure. Now, since this is validated for a single bottle, we moved on like, can we test these at the American Glass Research to see how they perform? So what you see here is 3 images. The one on the right is basically a package you receive from the glass manufacturer and in which the bottles are not damaged or used in any sense. Now, the one on the left, the line simulated ones, are the bottles which are damaged by having these bottles move through a line simulation or a line configuration. And then the second case is the manually abraded ones. These are bottles that are damaged by just hand usage or basically in shops or whatever. So that's the 3 configurations we have. We tested these after damaging them. So we tested the A1 and the B1, and we found the following results, is that the bottles which are line simulated have a maximum capacity of 16 kilonewtons, which is equal to a 4-door car, which is quite a lot. Yeah? The manual abraded one, even higher, 17 kilonewtons. Now, the one that's not damaged was around 21 kilonewtons. But what we saw is that indeed the biggest fracture happened in the shoulder and the heels of these bottles, which again validated what we have predicted here before. And the bottle thickness was also of other importance. And what you see here on the right is the student, Yunus Machi, who was actually damaging all these bottles by hand and testing them afterwards. So this is the mechanical behavior of a single bottle. And to move on to the following thing is the connections. So now we have knowledge about one single bottle. What happens if we move on to more? So as I have presented this before, the practice and the application of these bottles can be used in many ways. You can once again, present them or plant them in columns. You can make walls out of them. You can even, in some cases, make floors out of them. So there are a lot of configurations in which you can use these glass bottles. Now, we have focused, of course, on the columns, but just to give you a simple idea of how, for instance, for wall elements, you can take the bottles, you can place them horizontally, and then in between you could use a certain cementitious element or material in order to keep them together. That's something you can choose. However, this has quite some limitations. For instance, the height. So if you place these things, of course, horizontally, it takes a lot of material in order to create height. It's time-consuming, of course, the placing, but also at the same time, if you want to make these things dry. And of course, the material selection is also of utter importance. Think of the cementitious material. Which material is it? Is it durable? Is it sustainable, etc.? Because the whole idea behind this is that we want to be circular, we want to be sustainable and durable. So we should not create even more complications for us. But of course, the configurations, the simplicity of this application and the adaptability for wall elements is quite present. So this is for wall elements. And if you place these bottles horizontally. Now, if we place the bottles vertically, then you get like a lot of new configurations which you can also implement. Now, these are 8 configurations. I'll discuss them in sections. So now you have 2 bottles, 1 bottle. Actually, these are 2 configurations. 1 bottle is standing straight up with the top pointing upwards, and the second one is in which the top is pointing downwards. That's 2 configurations, and you can stack them on top of each other, of course. Now, the other configurations in which you have the bottles, but you cut them off at the shoulder. That creates, hopefully, some better connections between the 2 adjacent bottles. And in between, of course, you can always place rings. Well, you can use ones made out of nylon or plastic, or even out of steel material. Other configuration is in which you have, again, the full bottles, so not cut off, but in the middle you place a certain steel rod in order to keep things together. Then you, of course, need some molds, etc., to have them in place. And the last two is the same as the previous two ones, but with the cut bottles. And then, of course, you have also in the middle some steel elements in order to keep everything in place. Now, these are the 8 configurations that we looked at, and we went looking further into like what is possible. Well, as we see here, the full bottles in which the tops are mounted to each other and the bottoms are mounted to each other, and in the middle you have these steel rods going through the whole thing. And this is still a simulation. We haven't executed this physically, but what we have done is the following thing. We have looked at this configuration in which you have the stacked bottles once again. And you see here again the full bottles in which the top are attached to each other, and then you have plates made out of timber. You can choose any other material if you like, and you attach these to each other. And then you have this stacked configuration, which is nice because every level you can take off and then place it again in a different place or create a different configuration. Now, this is also the choice that we went through in investigating further whether this is something reliable and feasible to do. So we came up with 4 different configurations for that case, in which you have the first test is 4 bottles, single bottles, nothing on top of them. And then the second test is in which you have 4 bottles again per level, but then 2 levels. Then the third test is 2 bottles, or 2 levels of bottles, but then the heels are then attached to each other. And the fourth test is 4 bottles, 2 levels, but with the bottles cut at the shoulder of it. So these are not full bottles. We have taken these 4 tests. We have placed them in a shank machine, basically a pressure machine, to see how they behave. And what you see here is on the left, the 2 left pictures. These are the untested ones, and we have wrapped them with tape for safety reasons, but they didn't do anything to the strength or the properties of the material. And well, of course, when you have these machines working on these bottles, you have forces coming from the top and from the bottom, creating a lot of stress within these bottles. And on the right is the picture of the result, in which you see fracture, mainly in this case at the top, but the fracture also happened over here and also at the heel of the bottles. The numbers that came out of this is the following. So for the first test, we reached approximately 100 kilonewtons per unit, which is quite a lot. The second one around the 75 and 80. The third is around, again, 70 to 75. And the fourth one is the lowest. And the main reasons behind these is the imperfections. So what happened, of course, this is done briefly and not as accurate as we want. Of course, this has been carried out by a student. But in the future, we hope to reach better results. But what we've noticed, especially for the cut bottles, is that when you have these attached to each other and you've cut them, the slightest damage could create the whole package to fail. And that's the unfortunate case for especially the fourth situation. But in the future, we hope to improve. So this is for the results that we have reached with these simple tests at the moment. To go further to the limitations, because it's very interesting and there's a lot of potential in this application. The limitations are also quite a lot, because it's a quite new approach to everything. The first thing is the height tolerances. Not every bottle is exactly the same and exactly has the same height. So you have to really think about how are we going to deal with situations like that. So if we have bottles in practice and they are used and they come back in any way to the constructor, how are we going to make sure that every bottle fits perfectly next to each other in order to be able to have great tolerances? Then the capacity of bottles, at the moment, they're still quite fragile and weak. So it's something we can think about. Are we going to pose this question to the manufacturers of bottles in order to have an impact on society, in order to improve the bottles that we can use afterwards? Or should we come up with new methods in order to strengthen the bottles and make them have more capacity force-wise or stress-wise for actual application? Then the patterns. Now, we have presented 4 bottles next to each other, but we can think, of course, of a lot of bundles and different things and different methods and ways of how to connect these bottles. So this is an optimization problem, I would say. But it's also something to figure out, and also something that has quite a lot of influence on the behavior of a column. Now, the cost is always important, of course, to think about the costs. This is something we haven't really dived much into it yet, but we can imagine that it could be labor intensive if you haven't found a easy method yet in order to create such columns, for instance. But it's also something that we can come up with in order to make it more feasible for in the future. Now, safety, as you can imagine, it's very fragile, and glass can be super brittle. So especially in serviceability, when an actual column is standing, what happens if you, by accident, punch or break one of these glass bottles within a column? Does the whole structure then fail, or is something else being thought of to prevent that from happening? So it's also something that really needs some thinking from experts around the world. And then when a column or an element from a structure or a column is broken or damaged, what happens then? How can we prevent it from further damaging or further collapse? And this is something that also needs to be investigated further. We have given it some thought. We came up with like, hey, what if we can somehow create some reinforcement on the outside that in case one of these bottles fails, that the rest of the structure is still standing. And then, of course, next to this, you can come up and imagine more of these ideas for in the future. So, in conclusion, the question that I started with is how can structural columns be constructed with glass bottles? Maybe I should actually ask, can we at the moment? Yes, for very small buildings, which do not pose any safety issues and risks to any human being, but it has a lot of potential. And the potentials are indeed in thinking ways of how we can use, in this case, glass bottles, which is waste in a lot of cases, to implement them again in the structural world and in the built environment. Because the methods that I've presented, there are a lot of methods that we can still come up with and think how we can really introduce a whole new thinking about circularity and the whole approach of damage, safety, and also waste in order to make our world a bit more beautiful, use less resources, and more interesting for everyone around us. So as I said, this is a joint collaboration, and the lead was, of course, the student. So once again, thanks to him, and I want to thank all of you for your attention.